Hi everyone, we're starting chapter 7, and this is one of my favorite topics. I do think it's a challenging chapter. Have I been saying that a lot lately? That's just Gen Chem. But one of the things that's most challenging about Gen Chem is the way that we have to kind of switch gears. And so we have all these calculations of stoichiometry and everything where there's no equations. Then we have a chapter with some equations and some conceptual things and things we have to memorize and understand. And then we switch to a chapter where it's almost all conceptual and it's fairly abstract, and the kind of concepts that maybe take a little while to percolate in our brains. So there's only one real equation in this chapter that we're going to use for anything. There's some equations we talk about that we try and understand. But I do want to just stress that we're only doing the very first two sections of this right now. And so hopefully that will help. But in any case, this is the electronic structure of atoms, and this is our concept map where we have electronic structure, and what we mean by that really is orbitals, and we're going to link that up to the concept of the periodic table. And so our understanding, we did the periodic table in chapter 2, and our understanding of electrons. So electronic structure, what we're talking about is how do electrons behave in atoms, and what do they do, and what properties do they have? Because the chemistry is all about the electrons. Electrons are on the outside of the atoms, and that's where all the action is. That's where bonds are formed and ions and everything like that. So anyway, this linkage of concepts between our understanding of the electronic structure and orbitals, and ultimately electronic configurations, if that rings a bell for some of you from high school, and the way the periodic table is, and all the information that we know about the periodic table. So now it's important to understand the periodic table was figured out before, long before, well, before the electron was discovered, actually, right? And they were figuring it out just based on properties. So that shows again this idea we had in the last chapter of moving between observations on a macro scale to an atomic or subatomic, in this case, understanding of it. All right, so anyway, that's our setup. I love this topic. I think it's really interesting, and we'll see how it goes. So um, this is out of order, and I want to, I gotta have a place to set my pages here, sorry. Um, I want to just, we're going to come back to this, but the periodic table has these repeating trends, right? That's why it's called the periodic table, and we talked about that a little bit in chapter 2. But that's our ultimate goal here, is based on electron configurations and the understanding of orbitals and how electrons behave in atoms and energies, all the chemistry that we kind of memorized before, now we'll understand a little bit better. So this is a periodic trend where you see the size of the atom, atomic radius with atomic number, and you can see this repeating pattern as we go across the rows or across the periods. And like I said, this is at the end of the chapter, but I want to show the result of it first while we're kind of doing the explanation of it. So these are all the group 1 uh, metal ions, or atoms, sorry, atoms. I'm sorry, I caught myself misspeaking on one of the gas examples too, and then I caught it and said it right after that. But I don't know, maybe getting to be a long semester already for me. Anyway, so atoms, not ions. So the size of the atoms just repeats, where the group 1A are the largest, and then these are small, and it gets smaller as you go across. And what we're going to do is, by the end of the chapter, we're hopefully going to understand this trend. Why does the size go up as you go down the group, and why does the size get smaller as you go across the period? And these are the smallest ones down here. That's our group 7A. So that's what we're looking for, is how can we understand that based on orbitals in the atom. All right, so where's my next one? And you, of course, as I always repeat, you have this handout, right? So the electronic structure of the atom, there's two parts of this. We want to understand the interaction between light and matter, which is electrons in orbitals of atoms. So that's what we're really interested in this chapter. And when we say light, it's not just visible light that we can see. We're talking about electromagnetic radiation. And so in order to understand this interaction, we need to understand a little bit about the properties of light, and then a little bit about the properties of electrons in atoms, or the orbitals and electron configurations. And by doing that, understanding those two things, we can then come to understand how they interact. And in fact, it was through the interaction of light with the atoms, the electrons in atoms, that they kind of figured this out, right? They figured out the orbitals. And then the first question then, we're just, in this section, we're just going to talk about properties of light. That's all the farther we're going to get. And this electromagnetic radiation, you're probably familiar with this question: is light a particle or a wave? And if we were in person, which I really miss, I would ask this question of the class, and it's hard to say, what answer we would get, but usually once we talk about it, we would get this idea that it's both. And I like that idea, and a lot of, or that understanding of it. A lot of people would say this is the dual nature of light. But what this means is that some of the behaviors of light, of electromagnetic radiation, are analogous to a wave, water splashing. And then other behaviors of light are analogous to thinking of a particle, a small little packet, like a marble or something, only on a really, really small scale. And so that's the usual presentation, kind of, that it's both and that there's dual nature of light. Now, I tend to think, and I'm not going to get too deep into this. I don't want to. We just have to, understand it on a certain level. And this is where, it's hard for me whether I show my face and do this, but there's some of these where I want to draw and write things. But so it's a little hard for me to talk about this without looking at you and seeing you look back. But I don't necessarily think both is the best answer anymore. For me, anyway, in my understanding of it, I think of it as neither. So light is not a wave or a particle, in my humble opinion. Electromagnetic radiation is electromagnetic radiation, and it behaves the way it behaves. And we try and use our macroscopic understanding of large things, like, a particle that we can see moving, or waves splashing and interfering in a water tank, as a way of understanding electromagnetic radiation. And that's really good, and that's what we're going to do. But ultimately, light, or electromagnetic radiation, isn't a wave or a particle. It's electromagnetic radiation, and it behaves, there's this field called quantum mechanics. Oops, mechanics. And that's a whole chemistry course for chemistry majors and physics majors. Uh, and that's really explaining a lot more about subatomic, really, really tiny things, tiny particles and how they behave. So anyway, that's enough on that topic, but that's my understanding of light now. But we're going to talk about it as, it was historically kind of figured out, right? And so this is, let's see, zoom out a little. There we go. And this is a figure that your book did not have, um, but I like to look at this figure briefly anyway when we're going through light or electromagnetic radiation for the first time. So I got this off, Creative Commons license. It's actually from Wikipedia, which is the one that I could use that was shareable. And so electromagnetic radiation is just an electric field and a magnetic field, and it's those oscillations in the electric and magnetic field. And so they're perpendicular to each other, and hopefully this, kind of shows it going this way, electric field, magnetic field, B is the magnetic field. And so that is the oscillations going up and down in, and I don't know if you can see on the, I should have done a different color there. Right? And so those are perpendicular to each other. And that's how light, how electromagnetic radiation propagates through space. It's an electric and magnetic oscillation in some form. And this is then the figure from your book that shows how we treat light. And I think that I can get away with, can you see that? Well, you have the handout, so hopefully you can see that well enough. It usually looks good once it's on the YouTube, even if it doesn't look good on my screen. Anyway, so here's what we have to know for this chapter and for the beginning. It's just being familiar with the terminology, the terms and definitions of electromagnetic radiation. And so most of that comes from the wave behavior. So when people were arguing, let's see if I can find a sharper marker than that. When people were arguing about whether light was a wave or a particle, the consensus was at one point that it was a wave, and then they came up with an experiment that proved that it couldn't be just a wave. But anyway, so most of the terms refer to light with that come from the wave-like behavior. And so for instance, so the first one we have to know is wavelength. And so the wavelength is, right here from one peak to the other is a wavelength. And that symbol, and that's a lambda. And what we need to know about the wavelength of the light is the color. That's the way we tend to think of it. Now, wavelength is also related to this other term, which is frequency. And frequency is basically a V with a little extra pizzazz. And so that's a new symbol. And so frequency is how many how fast it oscillates. So you can think of this light wave, it's a sinusoidal oscillation in the electric and magnetic field, and we normally just draw the electric field oscillation, right? The earlier one showed both. And so it's going up and down. And we can look at this graph in one of two ways. We can look at it as we're standing here and looking down the light beam, if we could do such a thing, and seeing the oscillations up and down as a function of distance. So this could be distance, right? Hence the wavelength, or it could be time, right? And so time would be I'm a stationary observer and I'm watching this go by and the oscillation is going up and down and up and down. And that's what frequency is then. So these are related. So the frequency is the number of peaks that pass a certain point. I think I need to get sharper markers, don't you think? Per unit time. All right, so wavelength, frequency, we have to know the term, the symbol, and what it means, right? There's also, I guess I'll write that down here, amplitude. And the amplitude is just the size. It's how high those peaks are. So the magnitude would be another way of saying it. All right, now this is really not going to show up on here, but you have the book and you have the figure from the book, and so you can see the colors, hopefully, and it'll look a little bit better on yours. But every book has this, and you've seen this many, many times, I imagine. So it's the electromagnetic spectrum. And I'm not asking you to memorize the different wavelengths, ranges of all the different, and I know you can't even read these on here because the way it's showing up. But you certainly don't have to know the electromagnetic spectrum. So what we do want to know and understand, and once we have the equation, it'll be actually easier. So this is showing wavelength increasing this direction, right? Can't really see the arrow on there. And so the way this works is that if the wavelength is going that way, then the frequency is the other way. Frequency, so high frequency is over here, wavelength is, so it's small wavelengths, high frequency, large wavelengths, low frequency radiation. And then related to this is the energy. And once we have the equation, so the equation it'll make sense, of course, but I want you to know this relationship that the longer wavelengths are lower energy. And the higher wavelengths are high energy. And yeah, I think once you have the equation, you won't have to certainly memorize that. You can just look at it and see. But that means, like these radio waves, I know you can't read that, I'll write it in. The radio waves, there are all kinds of radio waves passing through our bodies all the time, right? All the different frequencies of radio waves from all different, not just the ones that we're making from radio stations, but all kinds of things, and where are cell phone towers, where do those show up? But those aren't harmful, right? They just pass right through us and nothing happens. But X-rays or ultraviolet rays out here, so this is UV and this is X-rays, they damage your DNA, right? And UV rays cause you skin cancer. Okay, and then the other thing that I think you're all very well aware of is that the visible light, and I know again I can't see it at all on here, but hopefully on your screen you can. the the visible light, the light that our eyes are sensitive to, is a very tiny slice out of the electromagnetic spectrum, right? And it's probably a good thing, because can you imagine how confusing it would be if we could see all of this? If you could see all the radio waves, all the different, radio station signals going around you and by you, it'd be crazy. And there's more than just radio stations that have radio waves, right? It's all tons of stuff. Okay, so I think in the interest of time, I'm gonna, well, it's hard for me to skip this, but I'm just gonna list off these things rather than showing it. And all of these wave properties of light. So wave properties of light are things like refraction, interference, or diffraction. And like I said, I love this stuff. I think it's really interesting. Uh, Refraction, that's the bending of light. I thought about just taking a jar of water and dropping a straw in or something. So, but you can do that, right? You've all seen the straw in a glass of water, and you see that, and you're used to that idea. But why does that happen? Why does light bend? That's kind of interesting to me. Um, and then interference patterns, diffraction patterns. So when you see a little bit of oil on a puddle out in the street, and you can see all those different colors, that's due to these wave properties of light as it's passing through there. And they're all kind of based on this idea of interference. So diffraction certainly is a diffraction pattern. And so interference, I'm going to attempt to draw this just because I do think it's important to understand a little bit why light seems to behave like a wave, and it has these properties that behave like a wave. So I'm going to draw some light waves, and let's see how well I can draw a couple of light waves. All right, not terrible, right? Kind of looks like my nose. And then I'm going to draw a second one, and I'm going to try and draw it the same way, starting in the same place, meaning they're in sync, and with the same wavelength. Okay? Not perfect, but assume those two are the same. So if you have two light waves that come together so that they're starting and stopping at the same time and position, and they have the same wavelength, they will reinforce one another, just like if we were had a jump rope and we were doing it synchronized, so it could make it go up and down, uh, or strings on a guitar or on a piano. But anyway, when you add these two waves together, what you get is just a bigger wave, right? And that's called constructive interference. And you can do the same thing where we have these same two waves, but what if the second wave was offset by that much and you add them together and then they cancel out, right? And that would be destructive interference. And constructive and destructive interference are what lead to diffraction patterns and all of that. And we don't want to go into it too much in Gen Chem, but I do think it's interesting how light behaves, and so I can't leave it out completely. Then the photoelectric effect. So the photoelectric effect is when they figured out that, well, maybe light isn't just a wave. So at that point, everyone, all the properties, all the behavior seemed pretty consistent with light behaving like a wave. And then there was this really cool experiment that they did that showed that, well, light isn't just a wave. I do want to show, because I don't think your book, I know your book doesn't have this, but this is a photomultiplier tube. And I'm going to talk about the photoelectric effect here in a second. But this is a really cool thing. It's used for detecting light in an instrument. You can see all these different metal leads here that are connected to a voltage source. Anyway, so light shines in here, and there's voltages across all these different electrodes. And when the light hits the detector, then electrons are emitted from that metal, and it just cascades down each one of these electrodes and keeps adding up more and more and more. And so that's a cool little device. It can detect light very, very sensitively in an instrument. So the photoelectric effect was the evidence that light behaved like a particle. And let's see if I can explain why that was the case. Now this is going to be hard. This explanation is in your book, and they do have a figure in your book, and the figure is the same as the cartoon that I've always drawn. But I think it's hard to just look at a figure. Sometimes I think it's better to draw it and think about it and talk about it, because there's some mental processing that goes on there. So here's the photoelectric effect experiment. So I've got a metal surface here that will represent that way. So I'll just write metal surface. So the metal surface is an electrode. We're going to connect a voltage to it. But on that metal surface then, we're going to shine some light. And so the light's going to come in. We'll make it red light. So we shine light on that metal surface. And if we do this in an evacuated tube, kind of like a light bulb, you pull the air out of it, and we have on this side another electrode that we're going to call the detector. So it's just an electrode, and we're going to apply a voltage across this. Pretty big voltage, hundreds of volts. And if you do this inside a vacuum, an evacuated glass tube, the light hits the metal surface, you apply this voltage, and what comes off of it, see if I can find another marker, is electrons. And those electrons slam into that detector, and we can electrons, so that's electrical current, right? And so we can measure the electricity, the electrical current that flows through that photomultiplier tube, right? And the electrical current tells us how much light hits the metal surface. So that's the photoelectric effect. It's really neat. I think it's awesome. But when they did this experiment, they got some kind of confusing results. Okay, so let's talk about those. All right, so a few things. First of all, the electrons that came off, the electrons that were ejected, didn't depend on the color of light. I'm sorry, they did depend, oh my gosh, they didn't depend on the intensity of light. All right, so here's where it gets hard for me to, if I misspeak, then I mess it up. So let's start over. Wipe that. I should go in and edit it, but I won't have time to edit it. So the electrons that come off depend on the color, but not the intensity. All right. So the electrons coming off depend on the color, which is the wavelength of light, but the electrons that came off or were ejected did not depend on the intensity. So that's really interesting, right? If light was a wave, you can think of a sand castle and you're splashing water at it. If you made the waves more intense, you would expect to get more of the sandcastle washed away. But that's not what happened at all. What happened was no matter how intense they made the light, they wouldn't get any electrons at all unless they were the right color. So that's kind of weird. So if the light was the wrong color, the wrong wavelength, there were no electrons. That's amazing, right? If it was the right wavelength, the intensity did increase the number of electrons. So intensity of the light did increase the current, but only if it was the right color. So if the wavelength was certain values. All right. So sorry that I initially, I started to say this backwards at the start and misspoke. So let's just go through it again and make sure everyone understands it. So here's the deal. You could have the most intense, the brightest light ever and get no photoelectric effect. But if you tuned the wavelength, you could get the photoelectric effect at certain metals, right? And every metal would be different. So what that means is that it's the nature of that light, the wavelength of that light, that determined whether you could eject electrons. If the wavelength wasn't right, you had no photoelectric effect. If it was right and you up the intensity, yeah, you'd get more electrons. All right, what does this mean in terms of what light must be? Well, if it was a wave, if you increased the intensity, the energy of the total light, it would have to give us electrons, right? But that's not what they saw. So what this means is that you have to have one particle of light with enough energy. Now, does that make sense to you? That the wavelength, then, the nature of that light has to be such that it can eject an electron. So one piece of light must have enough energy to eject one electron. All right, so that's the explanation of the photoelectric effect. And the photoelectric effect then demonstrated the particle nature of light, and then we call those particles photons. Now, here's the deal. Light still behaves like waves. These particles of light, these photons, still do all the behavior of waves. The interference, refraction, diffraction. All right. So then, ultimately, what do we have to know? Light is quantized. And what quantized means, and we said quantum mechanics earlier, quantized just means something that's countable, right? quantifiable. Light is a particle that also behaves like a wave, behaves like light, but we call that particle a photon. And then the energy of one photon, we've got an equation for that. And so that's where this came about. And we use the symbols from the wave nature of light. So E equals h nu equals hc over lambda. This is a really important equation. So we'll use it E equals h nu and E equals hc over lambda, and sometimes these two equal to each other. And let's just go through and identify and define everything. So E is the energy of one photon. Okay. Nu we already defined. That's the frequency. And that frequency is in per unit time, right? How many peaks pass by. And so it's per unit time is seconds to the minus 1. And we need to know those units. And then a second to the minus 1 is a hertz. Then H is the proportionality constant for this to convert from frequency to energy. And so you notice that the energy of a photon is directly proportional to the frequency, just like we did when we had the spectrum earlier. So H is Planck's constant, shows up all throughout science in different areas, just like pi or other things. So 6.626 times 10 to the minus 34 joules times seconds. So a really tiny number, right? Unbelievably tiny number. The photon energy is really, really small. All right. And of course, I give you this constant. You have to memorize that. Then C, you've probably used C as the speed of light before. So the speed of light, and I'll give you this value too. You don't have to memorize it. 3 times 10 to the 8th meters per second in a vacuum. And you know it slows down a little bit in more dense materials, but in air, it's still 3 times 10 to the 8th. It's not, you know, if you went out to enough sig figs, then yeah, it would be slightly different than in a vacuum. And then lambda, remember, was the wavelength. So the wavelength units, you know, it would be in meters when we use the speed of light in meters, but there's a lot of conversions that go on with the wavelength, because for convenience, if you're using radio waves versus visible light, you're going to use, people use different units on the wavelength just so that they're more convenient units. All right, well, let's do one calculation with this equation, and that's really what the chapter 7 part 1 homework is just calculations using that equation. So calculate the energy of a 589 nanometer sodium emission line. So we're always going to just go straight to this equation that I give to you. So we just have to be familiar with the goal in doing the homework problems for this part is just being familiar with all these symbols, what they mean, what the terms are, and then, you know, we're given the equation, so it's a matter of converting units and plugging in to solve for whatever's missing. So hopefully the calculations aren't too hard, but they're meant to familiarize us with the ideas of light, wavelength, frequency, and all that stuff. All right, so energy of the 580 nanometer sodium emission line. So since that's in units of length, we know that that's the wavelength, right? So I'm going to do it like this. E equals hc over lambda. And we'll just go ahead and plug in and do that. So what was that Planck's constant again? 6.626 times 10 to the minus 34th joules times seconds. And then speed of light was 3 times 10 to the 8th meters per second. And then the wavelength, I'm going to do my, I don't know if you remember me doing a shortcut kind of tricky way to do the conversion. I'm going to do it that way. 589 nano, a nanometer is 10 to the minus 9. Nano means 10 to the minus 9. So times 10 to the minus 9 meters. So this is nano. So I've just done the conversion by plugging it in that way, right? And let's go ahead and do that calculation then. Because our calculator can handle that just fine. We don't need to do the work. Let the calculator do the work. 6.626. Use the scientific notation button. It'll save you so much trouble. Minus 34 times 3 e to the 8th divided by 589. See that? No parentheses, no nothing, because if you use the scientific notation button, it's treating that just as a number, like number 3.5 or whatever. Anyway, and then so I did my conversion the shortcut way, and I do that, I get 3.37 times 10 to the minus 19th. And that now is in joules, because you see all the units have canceled, right? Meters canceled with meters, seconds with seconds, and now we're in joules. And that better be one of my answers. Yeah, it is. All right, so try the homework problems. I think there's 5 or 6 of them where you have to use this equation. There's also ones where you have to do it on a per mole basis, so you just have to use Avogadro's number, and hopefully that works for you. Let me know if you have any questions. Thanks, everyone.